Good afternoon, class. In today's video, what I wanted to do is to start a new section called waves. And this will include waves, sound, and light. So just know that that's where we're going. But for today's video, I wanted to cover just waves, the general form of it, because once you understand the general form, then the more specific versions of, for example, sound and light will make a whole lot more sense. So here we go. What is the general form of a wave? So a general wave will look like this, and for those of you who are a little bit higher in math, you might recognize this as it looks like a sine wave, a sinusoidal wave. And that's actually very true. Those are the few mathematical shapes or mathematical functions that you can actually see playing out in nature. Now, how do we break this down? Because there are certain parts to these waves that are very important to understand. For example, there are these places that, so this green line right here is going to be what we call zero amplitude or zero height. So this is the wave, this is where the wave height is, it's completely flat, or at least flat, at least relative to the rest of the surrounding area. So what we have here in this middle portion, where the wave dips and becomes zero again in amplitude, that would be the node. Okay, a node is a place where there is zero amplitude for any wave. So you actually have three nodes, one here, and one over here. Of course, if there are nodes, there are also what we call antinodes, or the opposite of nodes, which would be over here and over here. Now, of course, if you want to just think of them, if you want to simplify all of your thoughts and say, okay, there's nodes and antinodes, and just this is an antinode, both of them are antinodes, that's fine. That works. You know, I mean, it's not wrong to say that. However, there are some more traditional names for them. We call these peaks and troughs. So, you know, and of course you can think of them kind of like surfing waves, especially if you live near water or, you know, have access to a beach. You can think of the surfing wave. When the wave is coming over, you know, it's getting close to shore, it would be peaking, or as we would say here in Hawaii, it would be crest. The wave would start to crest and maybe start to, as we would say, barrel. But that would be the peak of the wave, the very top portion of it. And of course, on the other side of it, there's that dip in the water, where, you know, after the wave passes by. After a wave passes by, there will be a little bit like of a lower area of water compared to just still water, and that would be what we consider the trough. So those are ways to think about that. Those are just names, though. If you want to just use node and antinode, that's perfectly fine as well. So let's go over some other parts of it, because there is one more section of this wave that is actually really important, at least of the parts that I could draw. And that is this little bracket over here, because it's saying that from this part of the wave to this part of the wave is what we call the wavelength. And that is going to be very special, so I wanted to make sure that I introduced that the variable it's going to show, which is called the Greek letter lambda. Now, I know, you know, depending on which other, you know, what other writing systems you know, this may look kind of like maybe a Japanese or a Chinese character, but it's actually a Greek character, so it's the Greek letter lambda, lowercase lambda. So just wanted to make sure I clarify that before any confusion sets in. So now we need to talk about, now that we have a wave, we need to not only talk about units, but we need to talk about an equation that actually governs these waves, because they will be important, especially when we get into sound and light. And of course, as part of sound, we also have to talk about the specialized form of sound, which is music. So we'll be getting to those all those equations later, but this is the general form of it. So what are those units? Well, we've got wavelength. We already introduced that with our Greek letter lambda, and the unit for a wavelength, which hopefully should be fairly obvious, is meters. And of course, now we have to talk about the amplitude of the wave. I kind of mentioned that earlier, like as if I didn't without having to define it. I was hoping that maybe you would understand it as we're, you know, right at the beginning, but let's define it now. Amplitude is, if we think of this as the horizontal plane and the vertical plane, then while wavelength talks about how far the wave travels on the horizontal scale, the amplitude talks about how far the wave travels on the vertical scale. So how tall this wave is, or the distance from zero to the antinode, another way of thinking about it, would also be considered amplitude. If you're looking for an example to picture this, you can think of the wavelength kind of, well, the wavelength is the wavelength. Or it can be like the spacing, like if you're surfing and there are sets and there's a wave that crashes on the shore and then another wave. So the distance between those waves would be the wavelength. Okay, now what about the amplitude? That would be the size of the wave. Of course, if you're more musically inclined, you can think the sound of the wave, or the size of the wave, the amplitude, would be, in terms of sound, would be considered the volume. So the higher the amplitude, the higher the volume of the music. So then we got to the next. Now of course this is the last part of the units that we need to talk about, and this one is actually going to be really important, especially for those of you who enjoy music, because now we're going to talk about the frequency, because this is just one wave, and that's the thing. I couldn't draw all of the waves at this time. I could only draw this one wave just to give you the idea of what its structure is. But there are multiple copies of this wave traveling through this medium, whatever it is, even if it's the vacuum of space. And so how many of these waves reach you or reach their destination within a time frame would be considered the frequency. And that's why the unit for frequency is 1/seconds, which we have also come to the conclusion that we should also call it hertz. So for those of you who have ever seen, maybe you've tuned a musical instrument before, and you've seen that they, like concert A would always be measured at 440 kilohertz. Well, that would be 440,000 hertz, or that would be the number of wave. That would be the frequency at which you would hear these notes. So those are the units of a wave. Now there is one equation that's going to be very important, at least in a general form, and from there we'll actually get to more specialized ones, especially when talking about things like the speed of sound or anything like that. But this is what we call the wave speed. Now, of course, for using my surfing analogy, we're going to understand that wave speed would be very an apt description, because how fast those waves come, and crashing onto the shore is going to be very important for how we understand how the wave moves at all. Because frequency is nice and wavelength is nice, but if you don't know what the wave speed is, it's going to be a little bit hard to figure out how it physically would manifest in the real world. So the wave speed is going to be given by v, which is in meters per second, hopefully that makes sense, because that would be like any kind of wave that you might be experiencing in your everyday life. Of course, I like to use the beach, but that's because we live in Hawaii, or at least I'm filming this in Hawaii right now. So the wave speed is going to be given by the wavelength times the frequency. Now, one of the ways that you could picture this, especially for those of you who do have access to the beach and can see the ocean and all of the waves that come in from the ocean, what you can see is, and of course if you're a surfer, you might call them sets. So you might say, oh, like some people would say, oh, there's a great set coming. I can see, maybe they stand from a ways up and say, they look out and say, oh, there's a really nice set coming towards the island or towards the beach, and then you would have a grand old time surfing that set. What that really means is that there are a whole bunch of waves spaced out evenly, so that after you've ridden one wave, you can swim back out and ride the next wave, swim back out, ride the next wave in a fairly predictable order, where you get you can ride the most waves that you can while still enjoying your time surfing or swimming, whichever one it is. So that's the equation that governs how these waves work. And of course, we'll get into, in the next videos, we'll get into more of the specialized versions, like sound, light, music, for those of you who are so inclined. And so that would be the general structure of a wave. So that concludes this video on the introduction on the general form of a wave. Good luck in your studies. May the force be with you.